Okay, this is a continuous 15.6 surface integral. We're going to learn the vector form of the surface integral, okay? So before we do that, let me recall what we did on line integral first. On the line integral, and we are also scalar form, vector form, so I'm going to use the vector form to compare, okay? So the vector form is like this. Sometimes the people use a ds here, but I wouldn't do that, okay? Try to use a dr, because some people use it like I know you physicists, they use the s as a position function, because this represent position for the line integral. So sometimes they use s, but I wouldn't do that. I would just keep the r. So f dash dr, this means derivative with the position function, derivative r, okay? So it's equal r prime dt. And the rt is made up by syt, parametric equation, and dr means derivative of r, okay? Now we're going to change this to surface integral, okay? So line integral is a single integral. Now when you go to surface integral, it means it's integrate over the surface s, okay? So this is s here. And then, now this is a surface, right? And then if you 90 minus sum, you cut it, okay? So the little tiny here is a ds, okay? That means a little tiny surface. So the ds means very little, okay? So this is different than this one. This is derivative, but this not it. This means a little tiny surface. So they use a lowercase actually. This here, this is a big case, this uppercase, okay? ds, this one, is equal to the normal vector n times the this little ds, okay? So the big d, unfortunately I don't have like a big board, so this one is equal to n times the ds, okay? It's a derivative, it's a vector, because a vector times a scalar is still a vector, so it's a derivative of the area, this one, okay? It's a derivative with the small surface area. And then you will say a derivative with the small surface area shouldn't be a scalar. No, not here, because the reason is there is a normal vector for that, okay? Because the normal vector involved in, you say why is that? Because surface integral is about flux, okay? Cross means how much amount of electricity going through. So therefore, and also the speed they go through. So it's all together. So therefore, there's a direction there. So therefore, so that's why the ds, the big S here, okay, this is surface for the surface integral, okay, a derivative with the surface integral in this little tiny bit is equal to n times surface area. So this is the surface area, okay. So this is a vector. This is surface area. So this vector equal to n times that. So that's why I put here. So okay, the direction means that this equal that. And then this, the rotation here is still over the surface, so that's why it's s. Now then you go one more step down. That's also equal to, you convert it to r, the region you project it down to r, okay, and then will be f dots del g, okay. What's a del g? Del g is come from here, okay. If this surface function is given to you, okay, then you can let g equal to g subtract that. Why is that? Because surface functions are always in 12.7 at the 12. No, not 12.7. When we do the tangent at 13.7, wasn't it? And then the surface function always equal to 0 in this format, okay? So they have to put in this format, so that's why they subtract g, x, y, and then make it to be equal to 0. And then del g is a gradient for this surface function. So it's equal to take the gradient for x first, so negative gx, gradient for y is negative gy, and then partial derivative x is a negative gs, partial derivative y is a negative gy, and then z is a 1. Then the n is a unit normal vector, okay? So therefore, n is equal to del g divided by the length of del g. Now, if z is not given to you, or if your f that's a del g is too complicated to evaluate, then you must need to use the parameterized surface. I told you the second format, okay? The first format is this one. Second format is you parameterize surface. So sometimes this is not given to you parameter by u and v. Remember the uv plane? Or you can just, I just use the x and y, or you can use the uv. And like for spherical, symmetrical, they use a phi and theta, remember, or phi and z like that. So this is for g is equal to gsy is a given. Now sometimes you have a y here or you have x here, then you need to change this also. Okay, I'll show it to you how you change that later on. So let's go back to here. So that's where this comes from. Okay, this is just that. Okay, normal vector is just del g. You say, wait a minute, didn't you have for this one here? So it should be unit normal vector. Where that goes? This actually reduces that. Reduce with part of dA. I'll show it to you later on, okay? So right now, just take it as it is first. And then this come down to here. This will become this. If you're not using gradient to do the problem, you're using this way, normal vector by parameterize the surface, then the problem become like this, okay? Or can be different notation like I said earlier. So now I want to clear out some of the things that you guys may not follow. Is right here. Okay, first of all, why this will become this? So I'm going to show it to you. Okay, so I'm going to show it to you why that become this cleans a little bit better than the eraser. Okay, so now our goal is to, how come this become this? Okay, oh, wrong color. So once your S become R, that corresponds to dA. Okay, R and dA, S and ds. Okay. So NDS, it becomes del G dA. Why this is true? Because your N is equal to, okay, del G over the length of del G, right? And then your ds is a surface area. The formula for ds surface area is equal to 1 plus gx squared plus gy squared and dA. Okay, that is from when we do the surface area the last session, and then I tell you the formula for surface area is like this, and I use a G. The book use F, so that's fine because I use a G here, and this is the same as that. Okay, so this is the length. This is the same as, okay, the length of the gradient. So therefore this is reduced. So that's why it becomes just the del G over del G times dA. Same as that. It's a unit vector, but then also reduced with the length of the surface of the surface area, the portion of the surface area. So now if that's the case, okay, from now on you just get del G. You don't need to find this one, okay, because it get reduced anyway. So you just need to follow, just use this formula and use this formula, just follow. You do not need to convert, okay. That means you don't need to find the length because you're going to reduce anyway. So that's the number one thing you need to, I want to clear for you guys. Number two thing is that surface integral, okay, is also called the first integral. So if you read the book, or you watch other video from YouTube, and then you will see that that is also called the flux integral. Why is that? Okay, so sometimes we see people say, hey, flux integral, what they talking about? They actually talking about surface integral, okay? The application of a surface integral. So surface integral is also called the flux integral, okay? Flux integral, okay? So the definition is it measures the rate of a change, the rate of flow, measure rate of flow, so better say of a fluid across the surface S. Okay, and earlier it's equal to, okay, that's also equal to amount of a fluid divided by the unit time. Okay, that's why it's like a speed. Okay, speed is 20 miles per hour, like that, something like this. And so it's like how much, okay, how much fluid across, like how much heat across, how much electricity across per unit time. And so if so the F, so if F is a vector field or electricity field, like that, whatever vector field you're using, okay. And this actually is measured. So your surface integral, okay, the meaning have that is because your F, your vector field, so your vector field can be any kind, okay? Your vector field actually equal to the density time by speed. So that's why the time involved, okay? So this is density. So this is all physics stuff. And this V is a velocity. That's why when you have a F dots the del G, you end up have this, okay? Because the density, it means amount of stuff, and then changing, it means your speed, okay, your velocity. So amount times by the velocity per the unit time. Velocity have involved the unit time. So that is how you get the vector field. It's mainly for electricity, medicine. I don't know if I say that word right, mentalism. And then also for heat, and then liquid, okay? So that's why we have that formula. So that's how the formula gave you. Why do we get flux from that? It's because of this caused it. So that's why they say calculate flux integral, okay? It's the same as calculate surface integral. The reason is that I just gave to you guys. Now we're going to do some problems. Oh, one more thing. And this one is a normal vector, a uninormal vector. Okay. Now this vector, if S is a open surface. What is open surface? Like a surface not closed. Like for instance, this is an open surface, right? It's not closed. And your normal vector, it go by the positive orient. They say positive orient outward. Sometimes you've seen the book that positive orient outward. What do they mean by that? Positively. See, this is a if you teach in the class, it's much better because you guys can immediately answer me a question. Because right now I keep talking, I will forget things. So I will forget what I want to say. So this is a surface, right? Positive orient outward. What they mean is that counterclockwise we cast a positive in line integral because that's what we all follow. Okay. Outward means that you use a right hand rule, okay? Your finger pointing to the direction of the line integral going, okay? And then you go your thumb, okay? Your thumb is going up, okay? Then be upward. So this, or you can look at this. Let's say if you're walking right here, let's say there's you walking. There's another way to look at this. So let's say this is you here, okay, you're walking. When you're walking along the edge, make sure the S is on your, consistently on your left side the direction, okay. So you're walking consistent, so that is how they use the positive orient. So it's kind of like this, counterclockwise. And then that's your end. Your ends of your thumb, my thumb, okay, or going up. And so that's for open surface. But some students said, wait a minute, there's a downward also, right? If they use a downward here, then you have to use a negative end, okay? But the good news is most of the time I can teach you, don't need to memorize that because when we actually find a vector, you know it's going to be going down, then you're going to have a negative on the z direction. So that will take care of it. So that's for number one. If S is a closed surface, closed. What's a closed surface? Like sphere, okay? Like you have a sphere or hemisphere, whatever. That's a closed, right? So this is a closed surface, okay? Nice sphere, just an example, okay? And then now your end will always point outward. Okay, in this one it's always pointed outward. End's always outward because that's where your end is. Okay. Okay. You will always point it out because it's a closed surface, okay? So it's always pointed out. So that's your end. So this is all your end here, okay? So in that case, you don't have two direction. But you said, would they point it inside here? Okay. Well, that's usually is sometimes when we have the pumping stuff inside. So they do have that. So if you're pumping stuff like pumping air inside, pumping water inside, you do have two directions. Then you could have like this. Then the other way, okay, you're going inside. Okay. And when you're going inside, you'll be negative also. Okay. So again, I wouldn't have to worry about too much about it because when we actually set the vector, it will show up nicely. Okay, you will see. But sometimes they don't show up nicely, then you need to judge. Okay. If you're going to the way I look at it, if you're going to negative Z direction, because Z is so let's say this is my Z here. Okay, and that's my positive Z. So if I go into the positive Z direction, I'm positive. But if I go into the same, look at this. If you take one of them, that's your negative Z right here. Okay. If you have the same direction for pointing to negative Z, then it be negative. If it's like this one, this is a positive Z. Okay. Let's say I use this one. Then yeah, positive Z direction, you're going up. Okay, then you're positive. But if you're when you decompose the vector into two directions, the negative Z going down, okay, you follow the Z going down, then you have a negative. Sometimes they give you vector field like surface like that, vector field like that, they say pumping inside instead of going out. So this is going out. The red one is for going out, so it's easy to do because everything is positive. But when you have a inside, an inward one, okay, then it's a little bit tough, okay. Then you're going down. So when you're going down, then be negative. Actually, like this one, are actually going down also. Okay. And then you have to take negative also. So when you're upper top, but I never, well, you know, I wouldn't say level because this is mainly in the engineering, in the physics. For me, I only see vector field for half the hemisphere for math. But when you do the another half, that could actually, yes, I take it back. That could happen. Like cone. Cone is a tough one to do. Okay, if you are putting water inside here, and then you're gonna have going out, then you will have this, your N. Yeah, then you're gonna have a negative Z. Okay, so the best way I look at it is just look at negative Z, negative, positive Z, positive. That's the easier way to look at it. Okay, so now we're going to, so that's for the direction for N. Okay. This is usually the toughest one. So I remember when I was a tutor in community college with my engineering friends, and then they come over, they also say, hey, is my N's going to be positive, negative? That was a tough one to deal with. I just tell them to do like that. Decompose a vector and see if you're pointing to the positive Z or negative Z. Okay, so that's finished that. And most of the time we are positive here. Okay, in 1C class, you see negative occasionally in application of in some of the application class, like engineering course, then you might see the negative flow, negative on the end. So that's the first thing. Second thing, okay, is the first clause. So we only said that this one is N here, okay. Okay, and guess what happened here? You have a vector field, okay. Depending on how your vector field gonna go. So normally our vector field just any direction, right? So for instance, my vector field is cross like this, okay. F. And here's what happened. Because I mentioned last time, like Green theorem. Green tells you that, remember Green theorem has, now this we call Green theorem first. Green theorem said that if you have a co F, that's K, right? It's amount of circulation, right? So someone borrow the surface integral, they think that F that's N, it means something also. Okay, so look at co. Co is just also using right hand thumb rule. So if this is going like this way, okay, co will be also pointing like this, right? But we are not using co here. We are using the vector field function, vector field dots n, what did it mean to you then? Because this also vector dots k, it means something, right? So code dots k is like this. Okay, let's say this is, so this is my code here. And my k is like this. That's my k. So green things that code dot k, these two vectors dot to each other, it means it's something. Okay, let's say they both are, if they're going this direction, they both are pointing up. It means something, right? So do you think this one does that means something also? Well, it does. It means how much fluid you're gonna positive flow out or negative flow out or no flow out. So if f dots n is greater than 0, that means that if f dot n is greater than 0, that means that these have the same direction, okay? It means the flood is so that means the flood, this is number 1. Greater than 0 means that these two have the same direction. Okay, it also means the thrust greater than 0. So that means the two things here, okay? They both are pointing up. So in this case, they both are pointing up. And number 2, if f dots n less than 0, that means they're opposite direction. At least a dot here, okay? Okay, that means your thrust is going to be less than 0. And the last one, thrust less than 0 means they're going inward, going inside. Okay, more pumping in than going out. The last one is the thrust f dots n equal to 0. That means that f and n are perpendicular to each other. These are all vector here. I just didn't write it, okay? In this case, there's no thrust cross. No thrust cross. Okay? Means they cancel each other out. Like, how much go in, how much go out. How much go in, how much go out. I think that's what it means for physics. Oh, a cross. I spelled that wrong. Okay, let's see if I have any more I need to tell you guys. And I think that's it. Okay. So that is for all the information I think I need to give to you. Because without students to remind me, sometimes I just forget. And then I say, oh, after I finish the video, I say, oh my God, I forgot to tell students this. That's why sometimes I give you guys extra, I would say I have another video up. So I think that in a way it's okay because I don't mind to make another video for you guys. My goal is to have you to really understand this material because I know that it's so important for a student who's going to be an engineer, especially like electrical physics, electrical engineer, and there's another type of engineer need to take a class too. So one of my students told me at UCLA, he said the first day, the 2-hour class, the teacher, basically the 4th theorem I taught, it's all in the same day. He says it's really overwhelming, but good thing he had the notebook with him, so he was able to, to go through it. So now we're going to do some examples. Okay, so after I finish all this, let's try the vector field examples. The first example, number 26. we are given a vector field. Now remember, vector field is just a density times the velocity. Okay, and it's a surface, so the surface is given to you is g is equal to 6 minus 3x minus 2y. It says in your first obtain. What's the first obtain means? It means that x greater than equal 0, y greater than equal 0, and z greater than equal 0. That's what it means, okay? So first of all, you are given a surface function. If you give a surface function, I like to use a gradient to do the problems instead of parameterize my function. So I'm going to, before we do that, let me graph this surface first. So when I graph this surface, I go, when x and y equal 0, z is equal 6, there's a 6 here. When x equals, when y equals 0, x equals 2. When s equals 0, y equals 3. Okay, so they take just this little triangle here, okay, including inside. So the whole solid. So because the given surface is a function, so I'm going to use a gradient, okay? So you said the gradient always work, not always work. Sometimes it doesn't work, okay? It depends on the vector field also. If a vector field very complicated, when you adopt the gradient, it's maybe hard to integrate. So I'm going to find the gradient first. So that I'm going to let, okay, g is equal to g minus, remember g is equal to g minus this is small gx here, so the g subtract 6 plus 3x plus 2y, okay? And then I'm going to find the gradient of g is equal to gx, gy, gt. So gx equal to 3, gy equal to 2, gt equal to 1. So that's very nice. And then now I don't need to find a unit normal vector. The reason is because it cancels. Remember I showed you the example earlier, the formula, so it cancels that part out or reduce that part. So I don't need to find the length, okay? So now I take del g, f dot del g, okay? And your f equal to x, 2, y, 0, dots, this one, 3, 2, 1. It comes out equal to 3x plus 4y. That product, okay, 3x, 4y, and this is 0. Now we're going to integrate. When I integrate, I need to find the r. This is my region r here. Okay, and then I will draw the r region. R is basically when you look on the top and look down, you see this a triangle. That's a 2, that's a 3. My picture a little bit off, but it's okay. So I'm going to use a vertical cut. Okay, so my x will be from 0 to 2. My y will be from this one. You need to find the equation on that. Equation this one is g is equal to 0, so I solve for y, and y it comes out equal to 3 minus 0 to x, okay? Because your y is keep changing, so therefore it's this is represented by this function, not from 0 to 3. If you go 0 to 2, 0 to 3, you're looking for a rectangle, okay? So it's 0 to 3 minus 3 over 2x, and then integrate this one. And then dy dx, okay? And this is pretty easy. You guys will know how to do your iterate integration. So this is equal to, when I do it, it's equal to 18. So when I finish the integration, so this is your flux, okay? It means the amount of fluid or liquid or heat or electricity flows through. So if your physics is major, you probably use a lot too. One of my students at UC Davis, and he showed it to me his exam, they use a lot of a line integral. and differential equation. These are two classes they use the most. They hardly use Math 3. Math 3 is usually for students who major in computer software engineering like that. They use a lot of those. So it just hit across this one, okay, comes out. So if now you put this chunk of thing inside a vector field, well, how much electricity, let's say you put inside electricity field, how much electricity actually going across this whole surface, these whole things, okay? It's made up by 1, 2, 3, and then there's a piece here too. So it's a four surface actually. So that's how you do the problem. So it's 18 units. So we don't know what unit they use. So this for number 8 at 26. Now we're going to do another one, number 28. Surface integrals are not hard to do the problem, but there's a lot of things involved, like your normal vector. Well, the long vector we have earlier is pointing out, because all pointed out. So that's kind of nice. Oh, there's one more thing I want to tell you, okay, is that I forgot to mention. Good thing I forget. The picture I have earlier, okay? I said this is for this in the first obtain, okay? I forgot to mention that it's actually it's they gave us a first obtain means that you just cross here, but you don't include the x equal, you don't include this surface, okay? I forgot. They just said first obtain, okay? They didn't say include this one. They didn't say include s equals 0 surface or y equals 0 surface or z equals 0 surface. So therefore, when you find the first, you don't need to. You just need to evaluate this plane. Okay. They didn't say include this. That means you don't need to evaluate these three things. So I actually said only one surface, not three surfaces. Okay, only one. It's basically like this. It's against it. Okay, against it. So the liquid flows through, or the heat flows through here. Okay, they don't include that. I take it back. Okay, just this is surface. If they include these things, include these three things, you have to test them also. If they say, if the point given to you like n g x equals 0 surface, or x equals 0, n y equals 0, or n g equals 0, then you have to include testing these three things also. But they didn't say that. They just said first obtain. That's all they said. So that means it's a hollow. I forgot. That was my mistake. Good thing I catch it before I erase it. So it's like this. Okay, they like this. It's just a cross like that. Okay, not including inside, not including the surface here. The side, the bottom, and the other side, not included. So I take it back. Okay, just the surface here. Now, sometimes they will include it, okay? I will show it to you what happened when they include it later on, okay? Then you're not that lucky. Then you have to test all of them and then add them all together, just like line integral. So the last part is number 28, okay? And this one I want to do two different ways. The surface function, so the vector function, okay? Vector field function equal to x, y, z. This is pretty easy. They gave you a very easy vector field. And they said the surface is made up by a sphere, x squared plus y squared plus z squared equal to 36. They also said first obtain again. Again, first obtain means that this is it's like a, so let's say this is my sphere, okay? It's supposed to be like this, right? Now they cut down this part, okay? They cut down this part. So it's only take the first portion of it. Okay, and it's a hollow. It's a hollow. The reason it's a hollow, they didn't tell me take the z equals 0 plane or y equals 0 or x equals 0. They didn't say that. So it's like a hollow. against like a hollow things, okay? And so that's good. That means you don't need to test in the lattice strip plane. You just need to test the surface on the top, okay? Just this part. So I'm going to, because this is a function given to me, so I'm going to try to use a gradient, do the problem first, okay? And if the gradient doesn't work, then I try the other way. So I'm going to solve the GL. Surface function. I'm going to solve for G first. So G comes out equal to 13.6 subtract x squared subtract y squared. Because I only take the first obtained, so it's supposed to plus minus here, but I don't have the bottom part, so I just take the positive, okay? So my region R, it looks like this. Okay, just this part. This is x, and that's a y. So now I'm going to find the gradient, okay, the gradient. So I need to find the surface function first, equal to g subtract, okay, and the gradient g is just equal to, so take the derivative with respect to x, so that be negative, there's a negative here, okay, so that be negative, and then there's a 13.6 minus x squared minus y squared, and then respect to x is a negative 2x here, okay, and then for the same for y be negative 2y. Oh, I forgot the negative slide here also, because the negative here, right? So 13.6 minus x squared minus y squared. And for the g just equal 1. Okay? And then this can be, oh, I forgot a 2 here, I'm sorry. Whew. See, that's one thing I need you guys to remind me, because I forget. Now I have to, when I make a video, I have to be super careful, make sure I don't make any small mistakes. And then, so that's my gradient, okay? So now I'm going to take the f dot del g. Again, you don't need to normalize it, because remember, the formula reduces it for you. So my f is equal to syg dots by this chunk, okay? So I'm not going to write it again. So guess what happened? I get x squared, and then over 13.6 minus x squared minus y squared, and then plus the second y squared over the same thing plus, and then g, okay? And then when I add them together, I will get, so I have to erase this part. Well, I don't need this anymore. I mean, so this is continue 28, okay? So I simplify this one, okay? LCD here, so it comes out equal to, I also able to reduce that. So g here's g is equal to this, right? I erase that. G is equal to that. So this become x squared plus y squared plus g is equal to square root this. So square root, same thing, multiply each other, just becomes 13.6 minus x squared minus y squared over, and that cancel, okay? So that's equals 13.6. So that's what I get. And then I just need to calculate first by using the Jacobian changing, okay? It's a sphere, so that's pretty easy. So the first is just equal to first quadrant 0 to 2 power 2, okay? And the radius r is equal to 6, okay? R is equal to 6 because 13.6 is a 0 to 6. And then I compute 13.6, this would be 13.6 minus r squared, and then r dr d theta. And there's no theta there, so this can take away, so it's just a power 2, and then integrate that one. It comes out equal, just use a new sub, okay? It comes out equal to multiply the whole thing, it's just equal 108 pi. So I'm going to tell you my answer. You guys already know how to do your u sub here, right? U equal to this one, okay? So that's equal to u. Oh. Okay, so that's how you do if it's if you're able to find the surface of function. But this time you get lucky on this problem. Why is that? Because you're able to cancel everything out here, so you get a very nice number comes out. But you know what? It doesn't always act like this, okay? So sometimes they have vector field and you're not able to cancel anything out, then become very complicated. In that case, I probably wouldn't want to use the this way to do the problem, okay? Then you probably gonna have a little bit hard time to integrate sometimes. So, well, you know, not like, let me say like this. It's not like every time you're gonna get nicely comes out able to. What about if they have like x squared plus y here on the top, and then you're gonna have a complicate now, okay? If you don't have a number instead of some kind of variable, that means that you need to convert that variable to be r cosine theta also, and then you may not come out this nicely to integrate, okay? So I don't know. I mean, I tried it before. I remember sometimes it's not that easy. So therefore, there's another way to do the problem. We're going to parameterize the surface. Okay, so we do this problem by other way. Remember, pretend that we don't solve for z out. Okay, so this other parameterize this other method. It's a parameterize surface. Parametric the surface. Okay, so when we parametric surface, we are going to, okay, because we're x squared plus y squared plus z squared equals 36, right? And this is a sphere, okay? Sphere, we know that parameterize the sphere, we use about phi theta, okay? Is equal to 36 comes underneath the x, so it's 6 sine phi cosine theta. The one I gave you on 15.5, okay? And then 6 sine phi, and then sine theta, okay? And then 6 cosine phi. So we use this one. So let me erase this. And then I'm going to take the r phi now, okay, r phi. And then that will be equal to save time, I'm going to just, because I don't want the video too long. So I already did it earlier. So I will just, okay, I just tell you 6 cosine phi cosine theta. Just take the derivative, okay? 6 cosine phi sine theta. And then it's a negative 6 sine phi. Okay? And then I take the positive with respect to theta. So it comes out equal to negative 6 sine phi sine theta. Take this one, okay? So it's a negative because of cosine. And then that becomes 6 sine phi cosine theta. And this is a 0, okay, because there's no theta here. So now we're going to take the cross product. That's where you get your n. Remember, your normal vector comes from here now. Your n is equal to r phi cross r theta. And that's I. If you use this way to do, you guarantee get something, okay? Because this is kind of like a quadratic formula for solve quadratic equation. This parameter, the surface usually work for every problems. And the other way, it just work for if there's a a couple conditions have to be there, okay? The F has to be easy to find and easy to integrate and not that complicated, and then you're able to get the G out, and then take the dot product, that's all good. So it kind of like sometimes it's a hit and miss. If we like pawn number 26 that I did earlier, that's a perfect to use that way. Okay, I need more room. That one I definitely don't use this method. And this is a negative. And then I just put it here. I just move this down here, okay, 0. And then I take the determinant, it comes out after I cross them, okay, it comes out 36. It looks like pretty bizarre, but actually it's not too bad later on. And then the last one is I write right here. Okay, so after I take the cross product, then you need to parameterize the vector field. Okay, the vector field earlier. So I'm going to erase this part. My vector field is equal to x, y, z. Okay, then you need to put in your s, y, z here. And when I parameterize this one, s, y, z. Okay. Oh, well, it happened to be just this. Okay. So it just happened because they give us a very simple vector field. Okay, now we're gonna dot them. So I'm going to take the F, dot this one. So that's same with F, dots. Okay, and so this dot this, and it's just equal to, I simplify everything, okay, because I don't have time to go through all this. So it's equal to 216. I don't want to take too much of your, you've seen the video. Wow, that's a long video again. So, okay, just a dot product, okay, so you can, this dot this one, this dot this, and this dot this, and then simplify, that's what I get. And then I continue to simplify. I can take out 216, and then sine phi. Oh. And then I will have with sine square phi plus cosine square phi. And then so equal to 216 sine phi. And then now just integrate, okay? You integrate, use phi and theta, okay? So the first phi and theta, so d phi, d theta. So the d phi, d theta, because I took phi first. And then, so my theta, the graph I erased it earlier was like this, right? So my theta is 0 to the power 2. And my phi is also 0 to the power 2. My phi is the vertical one, okay? So let me show you the picture first. So that's my sphere, right? And this is your phi. Your phi is also 90 degrees. also 0 to the power 2, and 216 sine phi. And then you don't have a theta anymore, so it's a bit, that's gone, so it's equal to power 2 times by 216, and then comes as a negative cosine phi, and then 0 to the power 2, and that is equal to 108 pi, and that's equal to cosine, this is equal to 0, minus 2 minus become plus 1, so that's 108 pi. So this way to do it, usually you guarantee you will able to do it for sure, but the method can be long. But the other way to do it, that you may not able to integrate later on, okay? Maybe complicated to integrate, so that's the bad part about it. But if you can do it, it's very easy that way. So in the exam, I will give you a choice. Up to you which method you want it, okay? But you know, you don't have time to testing. That's the problem, okay? You don't have time to testing if the gradient gonna work. If you're able to integrate that, the f dot gradient, okay? So the problem comes right here. It is easy to integrate, or this is easy to integrate. Okay, that's basically, okay. This one, very easy to do it if you easy to integrate, but this one is not so, because you have parameterized the surface, but you're basically able to integrate. Okay, may not be right, may not be easy, but you're able to do it. But this one you may not able to do it, so that is the thing. And the last problem is number 32. I will just do a couple of them, okay, and then you do the rest of it. Number 32 homework, okay. So this is actual homework for your number 32. It's that you are given a vector field, because this one can tell the n, okay. I want to give you 4xy z squared and then yz, okay. And they tell that s is a unit q, okay, bounded by x equals 0 to 1, y is equal 0 to 1, z is equal 0 to 1. So it's like this. Okay, s from 0 to 1 is right here, y from 0 to 1, z is from 0 to 1, so it's a cube. Okay, that's a cube, and that's your 0 origin. I'll just do 3 of them. I'm going to do the back, okay, this one, the back, okay, and then I'm going to, so let's say that the back, okay, that's a x equals 0, right, because this is 1 here, this is your x here, so that is a x equals 0, okay. So I'm going to do that one first. So s equals 0, you're going to have a vector, okay. It pointed to out, because this is a closed surface, right? Closed surface, okay. And then they said it's a, let me see the, they say in exercise 13, find the first over the closed surface, and let n be the outward unit normal vector to the of the surface. So the book tells you all the thrust is going out, okay. So that means outward. So this is your n here, your normal vector, okay. So here's what you do. You're going to make a normal vector for s. This is n. You write down n is equal to, this is as a pointed out, so it's equal to negative 1. Your x is going the negative direction, right? Just my pictures, so it's a bit not very good on drawing, so let me draw this one. I want to, so Okay, so your n is equal to negative 1, 0, 0. Okay, your n is equal to negative 1 because you're pointing to the x, negative x direction. So it's going to be negative 1, 0, 0. Okay, and then your force is equal to, well, I'm not going to write it, so there's F dot n. That's very nice. F dot n is equal to what? Negative 4xy. And then I'm going to yeah, negative 1. The force is equal to then F dot n is equal to, oh, I forgot to parameterize the surface here. Let me see. Your yg F dot n equal to your force, yeah, your force, your F, because the S equals 0, and so I can do it right here. And then your S equals 0, so this just equals 0. So I was thinking do it other way, but that's okay. I could put it in at the end. Okay, so I put in S equals 0 here, so that means F dot n equals 0, that means no thrust. Okay, so no thrust, I don't need to calculate the first integral just equals 0. So that's my first one. And then and I'm going to do the other one. I'm going to go the left side, y equals 0 here. So y equals 0 will be like this. So I do the left side. Okay, left side here. So that'll be y is equal to 0. And y equals 0, and my n will equal to 0, 1, 0. Okay? Or negative 1, because I'm on the negative side. Forget the negative side here. So negative 1, 0, negative, 0, negative 1, 0. So my n is equal to 0, negative 1, 0. And then I'm going to dot them. F dot n, okay, F dot n, so I have a negative g squared. Well, negative g squared, there's no y here, so you're not that lucky. You have to integrate. Okay, to integrate this one will be, I put the negative sign outside, and I need to have SG plane, because this is on the SG plane, right? So this is a left side, y equals 0, so I put on my SG plane. Okay, so that means you have a ds dg here, and then negative g squared, and then x is 0 to 1, y is 0 to, g is 0 to 1. I integrate this one to put it straightforward, so I'm not going to do it. It's just equal to negative 1/3. Okay, so you can see this is the flow is a negative. If this is a negative, that means your first is negative, right? So I gave you guys earlier, okay, when the F dot m is less than 0, okay, means you have a what? First is a negative. Means that F and n are as an opposite direction, okay? So that means that the flow is going that way. It's pointing in this direction. So the flows are going that way at this point. So the opposite direction, that's because you get negative first. And then the last one I want to do is the top. On the top. So I'm going to go erase this one, okay, for the top one. I want you guys to do the rest of what I didn't do, okay? I want to do the bottom and the right side, and so you go home to do this one, okay, and then this one, and the front, okay? So please do the other 3. So then for the top, the top's right here. Okay, that's my end. So I'm going to erase this because it's too much here. Okay, n equal to 0, 0, and then the long on the going point out on the z direction, so positive 1. So then your on the top is a z is equal to 1. The plane is z is equal to 1, right? Z equal to 1. Here's a 1, okay? So the plane is right on the top here. So just a z equal to 1. And on a z equal to 1, and then you are looking at the xy plane, okay? Because this is on the xy plane on the top, right? So parallel to xy plane. So now my n is equal to 0, 0, 1. My f dot n, that's very nice. I only have yg. And my g is equal to 1, so just equal y. And then now just need to integrate with respect to ds dy. Equal to 0, 1, 0, 1, because the rectangular plane, so it's 0, 1, 0, 1, and then y, and then dx, dy, or dy, dx, up to you. And then it comes out the answer equal 1/2. Okay, so that's the first for each plane. They behave differently. Okay, so on the top one, they actually have more outflow than inflow. Okay, so it means that the f on this direction, this is your n here, and the f also on this direction. Then you say, why the vector field like that? They do, because if you put a box inside the liquid go around the box in different direction. So that's why they're different direction. So in this one, these two are the same direction. So that's why they're more outflow than inflow. Okay, so that's for the vector field part. For the vector form of the surface integrals for flux. If you have any question, feel free to ask me, because I could forget something sometimes when I teach, when no student there to ask me question. Feel free, okay?